Okay, so let's get down to the main content of this course. Uh, so what do concentration inequalities refer to? What's the main purpose of this particular course, right? So the phenomena of concentration is, you've already seen some of this in your probability course. So suppose I have a fair coin and I toss this coin n times, right? If n is very small, then let's say n is equal to 1, then with probability half you get a head, with probability half you get a tail. So you have two outcomes, both outcomes are equally likely, and you can't say anything more about the outcome of this particular event, right? But now suppose that I take the coin and I toss it a huge number of times. Let's say I toss it 1,000,000 times. Then what can you say about the fraction of the time you get a head? Right? Or the number of times you expect to see a head? Yeah? It's not a trick question. Half of the time, right? So roughly half of the time you expect to see a head, roughly half of the time you expect to see a tail, right? But this phenomena kicks in only if n is really large. If n is not too large, let's say n is equal to 2 or 3, then you don't see this happening. But as n becomes very large, you expect to see that the fraction of heads is very, very close to a half. And the larger n is, the larger is the more certain you are that the fraction of heads is going to be close to a half. And this is, in a way, formalized by the weak law and the strong law of large numbers. All right. So when I say concentration, it means that although the space of outcomes could be very, very large, in high dimensions, it so happens that much of the probability is concentrated in a very small set. Right? For example, when you're tossing coins, the fraction of heads can vary anything between 0 and 1. Right? But as n becomes larger and larger, with very high probability, you will see that the fraction of heads is very close to half. It's going to be somewhere in the neighborhood of half. And this is exactly what I mean by concentration. A lot of the probability concentrates in a very small subset. And the goal of this course is going to be to derive bounds on such probabilities. Right? So, more specifically, for a large part of this course, we'll assume that I have n random variables, all independent and identically distributed according to some distribution, some known distribution. So if we have this, then what can we say about the empirical average of these random variables? Right? What does the weak law of large numbers say? Right? What can you say about 1 by n, summation I equal to 1 to n, xi? Correct. So the weak law of large numbers says that this empirical average converges in probability to the mean, right? The expectation of x. The goal of this course will be to derive bounds on how close this empirical average is to the expectation. All right. In particular, so if I fix a particular epsilon greater than 0, then what is the probability that this empirical average deviates from the expectation by an amount epsilon? All right. And I want these bounds to hold true for every n. The weak law of large numbers or the strong law of large numbers, they tell you that the empirical average is going to be very close to the expectation as n tends to infinity. But it does not really make any predictions for finite n. Our goal will be to derive bounds for finite n. All right. But we'll try to generalize this a little bit further. We're interested in not just empirical averages, but more generally some function f of x1 through xn for reasonable functions. All right, I can't get bounds for arbitrary functions, but for certain classes of functions, we'll try to again derive bounds on the deviation between this function of x1 through xn and the corresponding expectation or some particular value. All right, and we'll see, and in particular, what I'll want to show or what we'll study are classes of random variables for which these probabilities decay exponentially in n. All right. We'll see more of this. I'll make it more formal as we go along. But by and large, that's what we're going to see in this particular course. Right. For different classes of random variables, we want tight bounds on probabilities of this particular form. All right. That may seem very specific, and you may wonder, well, what's the motivation behind studying some quantities? Because this is a very specific probability that we're looking at. Why is this useful? Right. We'll see a lot of examples in the course, but this has applications in a wide variety of areas, primarily statistical learning theory, which will be the main motivation for us. So our goal will be to derive bounds on the performance of certain machine learning algorithms. All right. So suppose that we don't have any constraints on computational complexity, and I give you some particular algorithm. I want to derive bounds on how well this particular algorithm behaves. All right. And these concentration inequalities can allow us to derive tight bounds on the performance of such algorithms. We'll see how that happens. We'll also see applications to not just supervised learning algorithms, but also certain unsupervised learning problems, such as PCA and as well as dimensionality reduction. If you've not heard of this before, don't worry. But loosely speaking, suppose that I give you a bunch of points in a very, very high dimensional space, then is it possible to project these vectors down to a lower dimensional space while still maintaining some sort of properties in this lower dimensional space? In particular, is it possible to project a large number of high dimensional vectors down to a lower dimensional space while still maintaining the pairwise distance between them, or approximately maintaining the pairwise distance between them? That's what I refer to as dimensionality reduction. And we'll see that these concentration inequalities can let us or allow us to know how much can the dimensionality be reduced. All right. So that's one broad area where concentration inequalities are useful. Another broad area where concentration inequalities are useful is in communications. Communications information theory. Again, I'm using communications in a very broad sense, and it corresponds to both point-to-point communication as well as data compression and so on. So in all of these, you can use concentration inequalities, and to give a very high-level sense or intuition behind why this can be useful in communications, it's the following reason. So suppose that suppose you want to communicate or send something through a noisy channel. So you have some signal X, and you're transmitting X through a noisy channel, and you receive Y, which is X plus, let's say, Gaussian noise. All right. No, there's not much that you can do over here. It's some corrupted version. But now suppose that I repeat this so-called experiment a whole number of times. All right. Instead of sending one signal, so just for simplicity, let me assume that the signal is a real number, all right, a random variable perhaps, and Z is a random variable which is Gaussian distributed. The end goal is always to recover X from Y. Okay, that's the main goal in communications. Now, instead of using this channel one time, instead of transmitting one symbol, let's say that I transmit n symbols. So I transmit an n-dimensional vector through the same channel, and this n-dimensional vector is corrupted by an n-dimensional Gaussian random vector. And again, the components of Zn are independent and identically distributed. My goal is always the same. It is to recover xn from yn. Now it may seem that I've not done anything much, right? It should not be the case that this problem is any easier than the problem where I have just one single x and I want to recover x from y. But as it turns out, as you go to high dimensions, this problem, or the problem of designing a good communication system, can become easier. And one of the reasons why this becomes easier is the following intuition. So if you look at a Gaussian random variable, right, a single Gaussian random variable, you know what the PDF looks like. It looks like a bell-shaped curve, right? So it's centered at 0, but it's kind of spread out. But as n becomes large, if you take a Gaussian random vector, it turns out that as n becomes larger and larger, a lot of the Gaussian random vector essentially looks similar to a random vector that is uniformly distributed on a sphere. I'm saying this in a very loose sense, all right? But much of the probability will be concentrated in a ball, or in fact almost a sphere of a certain radius. All right. So the advantage of going from a lower dimensional object to a higher dimensional object is that you have more structure coming into the problem, because now you know that with high probability this noise vector is going to lie within a certain ball. All right, and that can be exploited to design a good communication system. We'll see how this helps in more detail as we proceed through the course. The concentration inequalities are also extensively used in theoretical computer science. So you want to try to derive bounds on the performance of randomized algorithms, and similar to what you do in communications and statistical learning theory, you can use these concentration inequalities to say something about, let's say, the running time or the accuracy of randomized algorithms. They're also used in physics. You can think of a physical system which has a large number of interacting particles, and you want to say something about how these particles behave. It could be, for example, a gas, or where you have a lot of molecules which are potentially colliding with each other, or it could be some kind of a magnetic substance where you have these molecules, again, where you have some kind of an external interaction and the particles also interact with each other. So all of these, essentially, in one common theme in all of these applications is that we have very high dimensional random vectors, and we want to say something about the behavior of these high dimensional random vectors. And as n becomes larger and larger, the kind, irrespective of what kind of interactions there could be, in other words, what kind of correlations there could be among the components of the random vector, you can still say that, or you can still make very accurate predictions about some functions of these random vectors. And that's going to be the high-level goal of this particular course. All right? By the way, please feel free to stop me at any time and ask questions. All right. So before we get into concentration inequalities, today we'll just recap basic probability. All right. So hopefully you've seen what a probability space is. Probability space is essentially a tuple. It consists of three objects. One is the sample space, the other is the event space, and the third is a probability measure that is defined on this. All right. So a sample space is nothing but a set. All right. And this set could be discrete, it could be continuous, it could be finite, infinite, doesn't matter. The event space is a collection of subsets of the sample space. All right. So my event space is some collection of subsets of omega. So I'll use 2 to the omega to denote the power set of omega. So 2 to the omega denotes the set of all possible subsets of omega. All right, so this potentially can be a very huge object. Is this any collection of subsets of omega, or does it have to satisfy certain properties? Okay, what are the properties that this has to satisfy? Yeah. Okay, can you say what an algebra is?
That's theta and the set itself belongs to that. And if A and B belongs to the set A union B.
Slow down. So what's the first requirement? The sample space belongs to the events. So the sample space is an event. All right. So omega should belong to F. What else? Yep. So it's closed under complements. So if A belongs to F, then A complement should also be an event. All right. What else? Yep. So if you have a countable collection of sets, and each AI belongs to F, then the union should also be a valid event. Right? Okay. So the event space should be a sigma algebra, and this is precisely the definition of a sigma algebra. All right. Question. Okay, and now the third object is a probability measure, and you always assign probabilities to subsets in the event space, right? And what are the properties that the probability measure has to satisfy? Okay, we'll be a little more precise. So firstly, the probability measure has to be non-negative. All right, so P of A should be greater than or equal to 0 for all events A. What else? Yeah? Or more precisely, what is P of omega? That should be equal to 1. Right? Omega is always always a valid event. What is the third property? Right. So we'll generalize this a little bit. So if I have a countable collection of events, A1, A2, and so on, all of them being mutually exclusive. So exclusive, then the union this is equal to the sum of the probabilities. Right? Any questions so far? Okay. So it could be finite. When I say countable, it could be finite or countably infinite. It's at most countably infinite. Alright. Okay, so the first question, just to make sure that we're all on the same page, why do we define the probabilities on F and not on the outcomes? Right, so omega is the set of all outcomes, F is the collection of all possible events, and typically you always assign probabilities to events and not outcomes, formally speaking. Although in certain cases you can do so.
All outcomes are not equally likely.
That doesn't matter.
Because we are interested to know about events, like how probable it is coming, like how much probability of it actually happening. Like if we just go to sample space, it will include all the combinations rather than a specific event that we have.
So what? Is there a fundamental reason why you cannot or you may not be able to assign probabilities to outcomes? So let's take two different approaches, right? I have two sets. One is the set of all possible outcomes, that's the sample space. And the other is the set of all possible events.
We should know the
Right?
we should know the interest of the interest. Yeah.
That's okay. I mean, I give you more than what you need, that's perfectly fine, right?
So there are such cases. There are some paradoxes which I heard. So if maybe there are let's say our sample space is some ratio numbers and the interest is needed. So where we are defining one.
Okay, this is a much more simpler reason. Yes.
Suppose you have a pinpoint dart
Okay.
and a dartboard.
Yes.
So the event would be the dart landing on a point on that dartboard.
Yep.
If you assign probabilities for all the darts, you can't assign anything other than 0.
Yeah. So basically, you just take a continuous random variable, right? That's basically what you're getting to. If you have a continuous random variable, let's say that is distributed from 0 to 1, the interval from 0 to 1, what is the probability that if you take a random sample from this, what is the probability that this random variable takes the value 0.2, 0, 0.3, 0.4, right? So no matter, so the set of all outcomes is the set of all numbers from 0 to 1, right? All real numbers from 0 to 1. But what is the probability of each individual outcome? It is 0, right? So in such cases, it's not possible to assign probabilities to outcomes. So in particular, whenever you have an uncountable sample space, it is not possible to assign probabilities to individual outcomes. That's precisely why you define probabilities on events instead. It makes more sense to say that the probability that this random variable will lie in the interval from 0 to 0.2. What would that be if it's a uniform random variable?
1 upon
It would be 0.2. Alright? So when you have an uncountable sample space, you will only assign probabilities to events, you cannot assign probabilities to outcomes. Alright? That's a fundamental reason. No matter what happens, you can always assign probabilities to events. But you may or may not be able to assign probabilities to outcomes. If your sample space is finite, for sure, or it is in general discrete, it's at most countable, then you may be able to assign probabilities to individual outcomes. All right? Okay, so that's one thing. And now, when you consider the event space, right? It's a collection of subsets of omega. One choice for the event space is the set of all possible subsets of omega. All right? Can you always take the event space to be the set of all possible subsets of omega? Okay, and why not?
Because if the sample space is countably infinite, then 2 power omega will be uncountably infinite.
So what? In particular, we're interested in experiments where omega itself is uncountable, right? So 2 to the power omega is going to be huge. That's not such a big problem. Yeah.
It should be
Probabilities to uncountable set such that it sums up to
I,
in the case of continuous and 0 to 1.
okay.
So the events, the F would be whatever 0 1.
Fine.
So we cannot assign probabilities to that set such that the sigma summation over probabilities of events sums up to 1.
No, but I don't want that, right? So I'm going to individually assign. See, all I need to do is assign probabilities such that these properties are satisfied.
But the third property might not satisfy it.
Why not?
Countable sum we have accounted.
That's okay. I don't know what happens to uncountable sums and I don't care.
So you can't assign positive probability.
Why can't you?
The summation over that will exceed 1.
Why?
So because it is uncountable.
That's okay, right? So again, I need to be able to assign probabilities to sets, right? To events in a manner that is consistent. That is, no, irrespective of how I choose these A1, A2, and so on, countably many. Take any countable collection of events, of mutually exclusive events. It should sum, the probability of the union should be equal to the sum of the probabilities. That is all that I'm asking for.
So that cannot be done when you are considering uncountable sums.
And why not?
So let's say you have 0 to 1.
Okay,
Consider sigma algebra objects.
fine.
You assign the probabilities.
Yep.
But how you can't assign the positive probability such that it sum doesn't exceed 1.
Why? Okay, have you seen this before in your probability course, or did you ask this question in your probability course?
So in that question, all the elements are mutually exclusive in second question.
In which? No. So again, it's this choice, right? I want to choose some collection of events, not necessarily mutually. Of course, they won't be mutually exclusive.
We only care about certain events, not every.
As I said, if there is more than what I care about, I don't have a problem with it, right?
So if they are not mutually exclusive, then it might happen that that a certain point, if it's occurring, then it may affect occurring or not occurring of another point. And if we are taking 2 to the power sigma, then we are giving independence of every point of whether it want to occur or not, being independent of other points.
So in general, F will have sets. So F is going to be a collection of sets that are not mutually exclusive, right? Because as we've said, as we've seen before, if you have two events, then the union of those two events is also a valid event. So obviously A1, A2, and A1 union A2, these are not mutually exclusive, right? So that doesn't happen. There's a more subtle reason as to why you can't always choose the power set. It basically comes from measure theory. Again, I don't want to get into the details. It's a technical condition, but it's something that you still need to know. That is, if you take omega to be an uncountably infinite set, then in general there is no way of assigning a measure, a probability measure, to the set of all possible subsets in a way that is consistent. Again, what do I mean by consistency? So So let's suppose that I take some set, all right, and I write this as a countable union of some events, all right, some collection of sets, mutually exclusive sets. So if let's say I take one set, say the set 0 to 1. There could be a number of ways in which I can partition 0 to 1 such that they're all mutually exclusive and the union is equal to the interval from 0 to 1. Right? Let me write it down. All right, let's take an event. I'll call this A. Is the interval from 0 to 1. Now let's say that I partition A into two collections. So A is equal to A1 union, A2 union, A3 and so on. All right, so some countable collection of unions. And A, I can also partition it potentially in a different way. So this, let me I equal to 1 to infinity AI to 1 to infinity AI prime. So let's suppose that I take two different ways of partitioning the same set. All right. So just as an example, I could write A as a union of the interval 0 to half and half to 1. I can also write this as a union 0 to 1/3 union 1/3 to 1. Right? So there are, given the same set, I can partition it in a number of ways such that they're all mutually exclusive and the union is exactly equal to A. Consistency means that no matter how I partition them into valid events, mutually exclusive events, the sum of the probabilities of these AIs or AI primes should give me the probability of A. So irrespective of the partition, the sum of the probability should be exactly the same. All right. So basically we want summation I equal to 1 to infinity probability of AI prime. Alright, no matter how I partition, they're all mutually exclusive, but that's the only requirement. And each AI has to be a valid event. Alright. Now as it turns out, if you take the power set, then in general, there could be two different ways of partitioning some sets such that the sum of the probabilities are not the same. That is, there is no way of assigning a measure such that this method is consistent. All right. The way you construct these sets is not simple to describe. So you can just look up the following. Vitali set. All right. You can just look up what the Vitali set is. It's a construction of some set such that you can partition this set in two different ways, and the total probability of this set is going to depend on how you partition. All right. So basically taking the power set leads to these complications. All right. So the natural question is, how do you assign, is there a natural way of assigning probabilities to events? Because as you rightly pointed out, you can construct if you take the event space, then this in general is going to contain uncountably many sets. There are uncountably many events. Because if omega itself is uncountable, then the collection of all possible events is also going to be uncountable. So how do you assign probabilities? So one natural way is to generate the event space in some particular fashion. All right. So for example, let's say that my omega is either the set of all real numbers or some interval. All right. Just for the sake of argument, let's say that my omega is some subset of the real line. All right. What is a natural way of assigning probabilities? Let's take 0 to 1. Okay. So one natural way of assigning probabilities is assigning probabilities to contiguous intervals. All right. That's fairly easy to do. So in particular, I will assign probabilities to sets of the form 0 to a. To define the probability measure, I will assign probabilities to events of the form interval 0 to a. Okay. And now I'm going to consider the sigma algebra, the smallest sigma algebra that contains all these contiguous intervals. All right. So F So you choose F to be the smallest that is the smallest collection of subsets of omega which satisfies all of those three properties and contains all possible sets of the form, say A comma B, all contiguous intervals. All right. Does this statement make sense? Are there any questions? So right now my goal is the following. I want an intuitive but a non-problematic way of assigning probabilities to events, particularly when my sample space is the set of reals. Okay, or more generally, it's uncountably infinite.
So what does smallest sigma algebra mean?
So a sigma algebra is any collection of sets, of subsets of omega that satisfies these three properties. Right? So this is a sigma. So a sigma algebra is any collection that satisfies these three properties. So it's the smallest collection of sets that satisfies these three properties. So if you want to think about it constructively, then you take the collection, you take all possible sets of this particular form. That gives you one collection. And now what do you do next? You take complements of all these sets, because that also has to lie in the sigma algebra. So you add all the complements. And then you take all possible unions of all the sets that are present. And then you basically repeat. All right? That's one way of thinking about it in an intuitive way. All right?
So when you are saying that for uncountable sets,
Yes.
the probability measure cannot be consistent
If I take the power set.
if we take the power set.
Yes.
So someone was saying that if we take the power set, we cannot add all the probability measures and equal it to 1. Right? Like
Add the probabilities of which?
of the power
sets.
sets, like of all the sets in the power set.
But that anyway will exceed 1, right?
Yeah, it will exceed one.
Irrespective of whether you take the power set or not. Because again, if you go back to the definition of the probability measure, then it says that for any collection of mutually exclusive events, the sum of the probability, any countable collection of mutually exclusive events, the sum of the probability should be equal to 1. Right? And again, the collection of countable collections of mutually exclusive events is going to be a very, very small subcollection of the sigma algebra itself. Right?
When we are saying countable
Yes.
summation or countable union, we are considering all the mutually exclusive ones, right?
No.
Otherwise,
You take any subset of mutually exclusive events, then this should happen.
the thing is, could there be uncountable sets and then you only take some countable sets and prove this, and would that be enough?
So, for example, let's take the interval from 0 to 1. That's my omega, right? Now, if you take the events, all singleton events, 0, 0.5, 0.3, and so on. Now, these are all mutually exclusive. This is an uncountable subcollection of mutually exclusive events, right? This statement does not hold true for that particular subcollection, right? But if I take some countable subcollection, let's say the collection of all rational numbers from 0 to 1, this is a countable subcollection. The probability of getting a rational number should be equal to the sum of the probabilities of all of the rational numbers, which are all 0, which happen to be 0. So the probability of getting a rational number is 0. Right? So it only this statement is true only for all possible countable subcollections of mutually exclusive events. And there could be uncountably many ways of choosing these subcollections.
So now, when we are saying omega is equals to 0 to 1 interval, so if we are taking a power set of the same, then would probability of the entire set equal to 1 or would it exceed 1?
It depends on how you are considering. So it depends on what kind of a partition you are considering.
No, it's not.
Right? So again, the problem is, as I said, there is no, if you take in general, if you take, let's say, omega to be the interval from 0 to 1, and you try to assign probabilities to the entire power set, then you will end up with these inconsistencies. Potentially, there could be a way of partitioning the interval from 0 to 1 into mutually exclusive events, such that the probability sums to something greater than 1. You'll get all kinds of nonsensical things. Because as I said, there are certain sets for which the probability cannot be defined. If you partition it in two different ways, then you'll get two different values for the probability of this particular set. All right? And what we want is that no matter how you partition this set into disjoint subsets, the total probability should always be the same, no matter how you try to calculate it. Okay. Any other questions?
And now here,
Okay.
sets of the form a comma b or 0 to.
In general, a comma b, but sure, you could just take 0 to a. All right. So essentially, you take some of these basic sets for which it is easy to assign probabilities. All right, and then assign probabilities to these. So you put these in your sigma algebra because you know how to assign probabilities to these, and then you take all possible countable unions and of these as well as of their complements. That generates a sigma algebra. And if you take your basic sets to be intervals, then this particular sigma algebra has a name. It's called So this is called the Borel sigma algebra. Alright, so typically when you do probability theory, you mostly deal with the Borel sigma algebra. Right? There's another sigma algebra which is almost the same as the Borel sigma algebra, the Lebesgue sigma algebra. So, again, all you need to know about the Borel sigma algebra is you take all possible intervals and take the all possible countable unions and complements of these intervals and their complements. And that generates the Borel sigma algebra. Okay? And that's because this forms a sigma algebra. That's a non-trivial fact. And it turns out to be the smallest sigma algebra. That's also a non-trivial fact. But typically, this is the sigma algebra that you mostly deal with. And you do not use the power set. You use the power set only if your sample space is finite or countably infinite. Question?
How do you know that the cardinality or the size of the Borel sigma algebra is smaller than the Gauss?
Because you can show that there are certain sets which are not part of the Borel sigma algebra.
An example.
The Vitali set, as I said, does not belong to the Borel sigma algebra. I mean, these examples are of even the Vitali set. It's kind of a pathological example. Most sets that you can think of will belong to the Borel sigma algebra. Almost all sets that you can naturally construct will be part of the Borel sigma algebra. Okay, so this is something that you should know. Again, a lot of these are going to be hidden under the rug. We will not worry too much about it. But this is a basic fact to know about the sigma algebra that you deal with. All right? This becomes more important when you talk about collections of random variables, sequences of random variables, particularly infinite sequences of random variables, and so on. There's a natural choice of the sigma algebra, but typically you don't worry too much about it because there is a natural construction of this particular form. All right?
What's the difference between those Borel and Lebesgue?
So the Lebesgue sigma algebra is, again, it's a technical difference. So the Lebesgue sigma algebra is a superset of the Borel sigma algebra and also contains more sets, all of which have measure 0. Again, it's not particularly, you don't have to worry about what exactly the Lebesgue sigma algebra is, but you will see certain references make use of these terms, so you should know what they mean.
Does Borel sigma algebra contain sets of measure 0 or
It contains sets of measure 0.
contains some additional sets?
This Lebesgue sigma algebra contains additional sets of measure 0, which cannot be written as a countable union of intervals or their complements. All right? Because a lot of the references are going to make use of these terms, so you should know what they mean. Okay. Any questions so far? Great. So now let's continue. What is a random variable? How do you define a random variable? Yeah. So a random variable, although the name suggests that it's a random variable, it's actually a function from the sample space to the set of reals. Can it be any function?
Set of all omega such that x of omega less than or equal to some c belongs to the A.
So basically, if you look at this, is after all a map, right? It's a function from omega to r. What you want is the inverse image of any interval of the form minus infinity to alpha, right? So this is basically the event that x is less than or equal to alpha. Right? So this should be a valid event. So there's an underlying experiment which is described by omega fp. Right? It could be something very abstract, but you want to represent this using real numbers so that we have a common framework to study all kinds of probabilistic problems. And essentially what this is saying is no matter what you do, this x less than or equal to alpha is always going to be a valid event. And again, this goes back to what we saw over here, right? The Borel sigma algebra. What this is saying is that no matter how you choose f, this f is essentially going to be mapped to the Borel sigma algebra on R. So that is why it is sufficient to just assign probabilities or know how to assign probabilities to the Borel sigma algebra. Everything else is going to be taken care of in the background. So f could be anything arbitrary, but you can identify it with the Borel sigma algebra because sets from f are going to be mapped to events of this particular form. Right? So there's an underlying experiment which may or may not have to do with R. Right? For example, if you're tossing a coin, so the outcomes are heads or tails, but then you could map head to 1 and tail to 0. That gives you one particular random variable. And the corresponding f could be the set of all possible outcomes. Right? Or it could be all subsets of outcomes. And each of these is going to correspond to subsets of R. But no matter what you do, this is always going to be a valid event corresponding to your experiment. Does that?
Isn't this always there?
Which?
This thing, where it is minus infinity to alpha when you are doing an x inverse. Won't it always belong to f? Like, is there,
That's because we are defining it in this particular way.
is there an example where it won't satisfy or else?
I could choose a weird looking map such that this is not an event, but then that would not be a random variable. Okay, so this happens for every alpha in R. So alpha is some real number. Because the experiment in principle need not have outcomes that are real numbers, but you still want to map them to real numbers. For example, tossing of a coin. Right? The outcomes are not real numbers, it's head or tail, but then you map this to real numbers, and that gives you this.
Why are you defining x inverse on a set? Should it be a real number?
Because sets or the events are what get assigned probabilities, right? So maybe let me take the following example. This will help. Okay. So let's go back to the problem of tossing coins. All right. We know what happens if you toss a coin finitely many times, n times. Let me consider a new experiment. I want to toss coins, let's say a fair coin, infinitely many times. Right, I have a single fair coin and I'm tossing this infinitely many times. How do I construct, how do I assign probabilities now? What are individual outcomes? There are sequences of, infinite sequences of heads and tails. Right? And now I need a natural way of assigning, I need to firstly identify what events are and a natural way of assigning probabilities to events. What do I know? So what is a natural way of, what are natural events that you can consider for which you can assign, for which you know what the probabilities are?
Number of heads or number of tails is less than a fixed number.
Number of heads, that's infinite, right? I'm looking at an infinite sequence.
Number of times heads coming together, maybe into a gap.
Again, the number of heads in general is going to be infinite, right? It's an infinite sequence of tosses.
But I can say subsequence that okay, 4 times a head coming to the center. I can just take that subset and then assign probability.
Can you be a little more precise?
It's an infinite sequence, but in that the subsequence would be there where heads can come, let's say 4 times. So I can split that.
Which subsequence again?
So infinite sequence head tails.
Yep.
But in that you can have a small window where you can have 4 heads together, and then a tail comes. So you can just look at those patterns and then.
Okay, so you're close, but basically you know what the probabilities are for, let's say, the first 4 tosses. Right? You know the probabilities that the first 4 tosses comes according to a certain pattern, or the first, 5th, and 7th toss follows a certain pattern. So for any finite subsequence of this infinite sequence, I can calculate probabilities. Alright, that's something that I know. Now, is there a natural way of mapping this to a random variable? Yeah. Average number of heads. And why should that, why is this the random variable you want to consider? But then remember that if you use that, then 2 different infinite sequences could potentially get mapped to the same value, right? Is there a different way?
You don't want 2 different sequences.
I want a 1-to-1 map between the outcomes of this, and
Two binary, first one is
Yep.
to multiply to 2 raised to 0, second toss to 2 raised to 1, third to 2 raised to 3.
exactly, that's a great idea. So let me identify a heads with a 1 and tails with a 0. So basically, for each infinite sequence, I have an infinitely long binary string. All right, 1, 0, 1, 1, 0, 1, 1, 0, 0, and so on. All right. Now I can think of this as a binary string, perhaps after a decimal point. That's one way to do it. So this is the binary representation of some number between 0 and 1. To be more explicit, suppose that this is x1, this corresponds to x2, this corresponds to x3, and so on. Then my random variable, I define the random variable x to be summation I equal to, let's say 1 to infinity xi 2 to the power minus I. Okay. This is the binary representation of some number between 0 and 1. do you agree that this is a one-to-one map? Hopefully there's no problem with that. Okay, great. So now the question is this a random variable? Right? So in other words, if I look at the set of all sequences such that set of all x such that let me call this g of x1, x2 and so on. So it's a set of all sequences x1, x2 and so on such that g of x1 up to the whole infinite sequence is less than or equal to alpha. For every alpha, does this correspond to an event? So let's take a specific example. Let's take alpha equal to half. All right, pick alpha equal to half. What is the set of all sequences such that this quantity is less than or equal to half? What kind of binary strings give you this less than or equal to half?
Either a 1 and all the zeros, or it's zero.
Yeah, so maybe let's say strictly less than half, just for the sake of convenience. Then basically it is a set of all binary sequences for which the first bit is equal to a 0. Right? Do you agree with me? So x, the event x less than or equal to or strictly less than half is the same as the set of all sequences such that the first bit is equal to 0 or the first toss is a tail. Which one? Fine. Doesn't matter what it converges to, but it is less than half, right? It's less than 0, whatever. 1 followed by all zeros, right? It's arbitrarily close to, but not. It is, yes.
Is it an infinite length sequence?
It's an infinite length
Your
sequence.
sample space consists of a finite size windows.
Yeah, the event space consists. Yep. And again, we're not assigning probabilities to outcomes. Remember that. Right? This is my event, the set of all sequences for which x0 is equal to 0. The first toss is a tail. That's a valid event. Let's take the set of all sequences such that the first toss is a tail and the second toss is a head. What does that correspond to? Or let's say both of them are tails, because that should be even easier. Less than 1 by 4, right? So I leave this as an exercise, but now, irrespective of which interval you take, right? You pick any interval from any sub-interval of 0 to 1, that is going to look something like this, right? You can write it in a similar form. It is going to be some subcollection of coin tosses, right? Some subcollection of outcomes, which you can describe explicitly, right? And again, just for these specific examples, what is the probability that the first toss is a tail? Half, right? And so which means that the probability of this event is half, right? What is the probability that the first two events, the first two tosses are tail? 1/4. So the probability of this event, the probability that the random variable takes something less than 1/4 is also going to be 1/4. You can extrapolate in this particular fashion. So remember that we have constructed a random variable from 0 to 1 that takes values from 0 to 1 using an infinite sequence of fair coin tosses. Right? This induces some distribution on the random variable x. I had a collection of infinitely many coin tosses. Using this, I have constructed a new random variable that takes any value from 0 to 1. Can you guess what this distribution is going to be on x, on the random variable x? Yeah? It's going to be uniform. Right? This infinite sequence of coin tosses is going to induce a uniform distribution from 0 to 1. It requires a little bit of thought. At this point, it's just a guess, but
Could you once explicitly write the event space?
I'm sorry?
Event space, could you just write it down?
The sample space, the event space.
Yes.
For this particular case,
Yes.
you might as well take the set of all. Okay, so the event space essentially consists of what I call all possible cylinder sets, which is any description of finite subcollections of these coin tosses. All right. So you specify I1, xi2 up to xik. Ik for all possible k, all finite k. So all finite subsequences of this infinite sequence.
Why is it in event space? Shouldn't it be sort of the
Okay.
set of 0 to 1?
You'll see that they're equivalent, but it requires more effort to show that they're equivalent. This is okay. I should say the smallest sigma algebra containing this, because it should also contain its complements, which
And
is
how is x less than half contained in f?
So x less than half consists of
Sequences.
starting with 0, right? Which can exactly be described in this particular form. Right? So that's x1 equal to 0.
Yes.
Sir, how did you come up with that summation actually?
It was more of a guess, because I know that it works in this case.
To define what did you
This is my random experiment, right? I wanted to define a random variable for this particular experiment, which means I need a mapping from infinite sequences to a subset of the reals. All right? And this is a particularly nice choice. I could have chosen it in a different way. For example, here instead of 2 to the minus I could have chosen something totally different. All right? And that would give me a different random variable which corresponds to a different distribution. But this is a particularly nice map which eventually gives me the uniform distribution from 0 to 1. All right. So again, these are two different experiments, that is generating a random number from uniformly from 0 to 1 and tossing a coin infinitely many times. But as you see, they have the same, they can be represented using the same random variable. So a random variable is to be understood as an abstraction of your random experiment. There could be multiple random experiments that correspond to the same random variable. But if you are able to study the random variable in a general fashion, then it's also equivalent to studying whatever complicated random experiment you have, which in this example could be tossing the coin infinitely many times. Because in general, this becomes difficult to study, right? Infinitely many coin tosses. If you want to say something about this, it's a lot harder to wrap our heads around this particular experiment. But a random variable that is uniformly between 0 to 1, we have more intuition about. So it's enough for us to derive intuition for random variables, because this can be carried forward to more complicated experiments. That's the power of the formalism in probability. All right, so just take a couple of minutes and then we'll wrap up. Just a point about notation. So typically I'll use small letters to denote deterministic values or outcomes which are real valued, capital letters to denote random variables, and vectors I'll either denote using a superscript when I want to denote the dimension of this particular vector, or if the dimension is well understood or if that's not particularly relevant, then I'll use an underline to denote a random vector or a deterministic vector. And capital, again, uppercase means that it's a random vector. All right. All right. So, as I said, as I alluded to earlier, for random variables, again, we can only assign probabilities to events, right, or the event space. And for a random variable, you always assign probabilities to events of the form -infinity to alpha, to be more precise, because by definition, these sets are always events. We are guaranteed that x less than or equal to alpha is always going to be a valid event. So the correct way of defining a probability of, but what is this equal to? This is a particular function, the CDF, right? And I will denote CDF using capital F, and I'll typically use the subscript to denote what random variable this corresponds to. Right? So it doesn't matter what kind of a random variable it is, every random variable will have a CDF, because these sets are always going to be events and probabilities are going to be assigned to them. Right? Now a random variable, continuous or if it's continuous, then it may or may not have a probability density function. Not all continuous random variables have valid probability density functions, but typically the probability, if this fx is differentiable, then the probability density function is d by d alpha So the probability density function is a natural way of assigning probabilities, although you're guaranteed that the CDF always exists. In many cases, it's more easier to work with the PDF. And for a discrete random variable, again, you use the probability mass function, which essentially, in a way, you can think of assigning probabilities to individual outcomes. All right? And you've seen what the mean and variance of a random variable is. We'll typically be interested also in higher order moments, which are expectation of x to the k or expectation of x minus the mean whole to the power k. We'll explore this in more detail, but what will come up a lot is the moment generating function, which is expectation of e to the power t times x for any t in R. All right. So hopefully you've seen all of this before, and we'll make use of some common distribution. So it's good to know what the corresponding probability mass functions, probability density functions, and so on. Okay. Any questions? If not, let's stop here.
This will be shared on Google Class.
This will be shared. The notes will be shared.